The mean value theorem, this is section 5.2, assignment 19. This theorem is one of the more important ones that we'll look at this year, and it will also have, it'll come back in a slightly different form when we're looking at integration in a few weeks. The theorem is important because it relates the average rate of change of a function over a closed interval with the instantaneous rate of change of the function. And it's stated as follows. So here's what it says. The function has to be continuous over the closed interval and differentiable over the open interval. If those conditions are met, then there must exist at least one value of c in the open interval a to b, such that the derivative at c is equal to the slope of the tangent line over that interval. And please notice that those conditions are absolutely essential. Here's a really simple example of a function which serves as a counterexample. So let's suppose we talk about y is equal to the absolute value of x over the interval, let's say -1 to 2. Now, you should be suspicious about this interval. Here's what we know. We know that f of 2 minus f of minus 1 over 2 minus minus 1 is equal to 1/3. And so we want to find a value of c in the interval -1 to 2 such that f prime of c is equal to 1/3. And when you think about the graph, here's a little tiny graph of the absolute value of x. One of the things we recognize is that when x is greater than 0, the derivative is 1. When x is less than 0, the derivative is -1. And the derivative never is 1/3. And the reason why this is a nice counterexample is that we know that at 0, this function, y equals absolute value of x, is not differentiable. So it fails to satisfy the condition that the function must be differentiable over the interval, in this case, -1 to 2. So before you ever apply the mean value theorem, it is essential that you ensure that the conditions are met. So in this case, let's look at a function which does satisfy the conditions of the mean value theorem. Here f of x is x squared minus 3, which is a polynomial, and polynomials are going to be differentiable and continuous everywhere. And so for this one, we want to look at it over the interval, say, -2 to 3. And so what we're looking for, what's promised by the mean value theorem, is a value of c in this open interval -2 to 3, such that the instantaneous rate of change at c, which is the derivative, is equal to the average rate of change for f over the interval -2 to 3. Now, we know that this shouldn't take you very long to determine that that's equal to 1. We also know that f prime of x is equal to 2x. So therefore, what we want is a c such that 2c is equal to 1, and obviously that means c is equal to 1/2. And ensure yourself, be sure that 1/2 is in the interval -2 to 3. So what we say is that 1/2 is the value that is promised or guaranteed by the mean value theorem. So let's take a look at the graphical representation of what the mean value theorem is saying to us. What I've drawn here is a continuous differentiable function over the interval connected by the points P and Q. And I've drawn the secant line, PQ. Now remember, the mean value theorem says that there must be a value somewhere between here and here, where the instantaneous rate of change is equal to the average rate of change. Visually, what that means is that there must be a tangent line which is parallel, in other words, the same slope as the secant line. And if we draw that, it looks like it's going to happen somewhere, let's get my little color here, somewhere about here. There we go. So it looks like, hopefully, that these two lines are parallel. And so wherever that point happened, which it would be, let's say right about here, that is what we would say is our value of C. And we have a couple of results from the mean value theorem that simply standardize what we've already known, which is that if the derivative is greater than 0, that happens exactly when the function is increasing. And similarly, if the derivative is negative, that means that the function is decreasing. And finally, if we have two functions where the derivative of one is equal to the derivative of the other, that only happens when one of the functions is really just a vertical translation of the other. So those are fairly simple implications that follow directly from the mean value theorem. It's worth noting in passing that the mean value theorem is what's known as an existence theorem. It promises, under the certain conditions that must be satisfied, it promises that a value C is going to exist. However, please note that it gives us absolutely no way of finding C. That's up to us. And here's another definition. And we say that big F is an antiderivative of, let's say, little f, if and only if, when we take the derivative of big F, we get little f. So we've kind of played with this a little bit, and what we'll look at next is an example in which this works. Before we begin the example, let's remember a little bit about straight line motion. If we have s of t, which is a position function, telling us where a particle is on a straight line at any particular time t, then we know that velocity is equal to the derivative of the position with respect to time, and similarly we know acceleration is equal to the derivative of velocity with respect to time. We've done quite a few problems in the textbook that use these relations. The next example will explore a little bit more about how we use antiderivatives to solve these kinds of problems. Okay, so here is an example of a very standard type of straight line motion problem. We have a toy rocket being shot upwards. Its initial velocity is 64 feet per second. Its initial height was 6 feet. And once it is shot, the only thing that's acting on it is gravity, which is acceleration. Gravity is minus 32 feet per second per second. So here's how we learn everything that we need to know about this rocket. We start with acceleration, which is minus 32. And since acceleration is the derivative of velocity, if we go backwards, velocity must be minus 32t plus some constant, because when you take the derivative of velocity, you'll get acceleration. Now, figuring out that constant is actually pretty easy, because if I let t be 0, then the velocity is simply what the velocity was when the rocket was shot, and we're told that was 64. So now we do this one more time, and we go to the position function. And the same idea works. The derivative of position is velocity. So if we have velocity, what we're asking for is what did we start with, whose derivative would be minus 32t plus 64. So once you know derivatives well enough, you can go backwards and figure out that the position function must be minus 16t squared plus 64t plus any constant. And similarly, that constant refers to the height when time was 0. And the height when time was 0, we're told, is 6 feet. So now we have equations for all of the 3 position functions. So now we can answer a question like, how high does it go? Well, we know that when it gets to the very top, velocity is 0. And it's pretty easy to see that velocity is 0 means t is 2 seconds. So how high it goes is simply s of 2. And a few minutes of calculation will tell us that s of 2 is 70 feet. So that's how high it goes. Suppose we want to know how fast is it going when it hits the ground. Well, it hits the ground when s is equal to 0. And if we solve the equation for s equaling 0, what we'll get is that t, in this case, is equal to about 4.09 seconds. And so the speed, that's probably the more appropriate question, the speed at impact is v of 4.09, which is about 66.88 feet per second. And that's the way straight line motion problem works. So that'll conclude this lecture on the mean value theorem. See you next time. Have a good day.